Today we're going to talk about Aristotle's universe. So who was Aristotle? Well, he was an ancient Greek natural philosopher. And I don't know the exact dates that he lived, but I'm going to say it's around 450 BC. Long, long time ago. Okay? And Aristotle was very kind of well respected, both in his day and going forward into the future. And one of the main reasons why is because he had a view of the universe that essentially explained everything about it. Okay, so we're going to look at the physics of this universe. So the first thing in Aristotle's universe is that at the center of the entire universe is the Earth. Earth. Okay, now you got to remember, this is 450 BC. This is like, I don't know, what is it, like the 2000s? Like this is like almost 2,500 years ago, like a really long time ago. So people's views and the way they thought, and what was true and what was everything like that was completely different from our views today. Okay, and the first thing that probably people noticed back then that we don't view as being true is they thought, and rightly so, that the Earth was completely stationary, right? When you go outside or when you're sitting where you are, does it feel to you like the Earth is moving at all? No, not right. It doesn't. And when you walk around, you can tell that you're moving, and when you ride on a horse, you can tell what movement feels like. The Earth does not appear to move, right? It appears to be completely stationary. So it's not hard to understand why it was Aristotle's view that Earth was stationary at the center of the entire universe. And then on top of the Earth, you had areas of water, right? So there's all your big oceans and so on. Okay, so we've got Earth and we've got water, and then above that there's a layer of air, right? And we can feel air, we can interact with air. You can stick your hand out the window of a moving vehicle, or in his day, I guess maybe while riding on a horse or something, and you can feel the resistance of air. And if you deprive someone of air, they'll die, right? Students? Right. Okay. So Earth, water, air, and then there's got to be something else to complete the picture, right? What's the last thing that goes with Earth, air, and water? Yes, fire. Thank you. I think dirt is covered by earth there, student. Okay. And so you know, fire is maybe up here where you have all these things scattered across the night sky. And you can also make fire on Earth. Okay. So there might be a relationship between these two things. And then beyond this sort of sphere, okay, you have the ether, okay, or the nothingness, or space, or whatever, okay, those guys thought. Now if you look up into the sky, you see that the stars move on circular paths. So the idea was that the stars were on this giant crystal sphere out here, okay, and that this crystal sphere rotated around the Earth, which stayed still, and that also up here in the sky were things like the sun, okay, and it also went in a circular path around the Earth. Um, then you had the moon. The moon moved around too. How exactly you had this set up, I'm not precisely sure. But then amongst these kind of stars that move on perfectly circular paths, you also have these planets that do these sort of wandering motions around. In fact, planetos, so I've been told, actually means wanderer in Greek. Okay, so this was Aristotle's universe, all right, and it was accepted, and he kind of tied everything that he said about the world into this view. So we're going to talk a little bit about the physics side of things, and specifically motion. So Aristotle's views on motion is what we're after. Okay, so Aristotle said there was two kinds of motion, two types. There's either natural motion or violent motion. Okay? So what's the difference? Well, if I'm standing on the surface of Earth, I take an object like a brick or something, whatever, right? And I let it go and I drop it. Well, what do we all expect to have happen? It does what? Yeah, it falls, right? Its velocity is towards the center of the Earth. Now think about this picture. The center of the Earth is here, okay? Aristotle has 4 elements. Oh, and something I forgot to mention is he thought everything is made up of ratios of the 4 elements. Now we know from chemistry class that there's a lot more than 4 elements, right? There's an entire periodic table full. But back in his day, we didn't have the chemical techniques that we have now. And it really wasn't until the Renaissance that scientists were able to prove the existence of more than 4 elements. Okay, scientists like Lavoisier spent their careers, basically pulling apart elements and figuring out that there's a lot more. A big deal was when they first created batteries, and Lavoisier was able to do electrolysis on water and pull hydrogen and oxygen out of liquid water. And you can actually do this in the lab today. It's pretty interesting. So you can get gas out of water. But in Aristotle's time, that didn't exist. So what Aristotle said was happening here was he was saying that the brick is going to be made up of earth and probably some bit of water, right? And so what's happening when you let a brick fall and it just falls to the ground naturally is it is returning to its natural place. The earth-water combination of the brick belongs in the earth, at the center of the earth, right? So it will naturally just travel there on its own, okay? Contrast that with what happens if you sit a brick on a surface and you want the brick to move in this direction. What do you have to do in order for that to happen? Student in the back. Yes, you have to push it. Okay? So here, there's no push required, right? The object just naturally goes to the earth. Here, you do have to push. A push is required. Or if you want, a force must be applied to keep this brick moving. Okay? So Aristotle called this violent motion. It's violent because you have to violently make this thing move, right? This naturally happens. This is violent. It seems logical, right? Makes sense. And you might also have noticed, Aristotle might have said, okay, like if we say build a fire, right? Coming out of the fire, you're going to have, this is my fire, you're going to have what? What comes out of fire? Ash and smoke, and it goes up, right? That fits in too. Air and fire are up high, right? Earth and water are down low. Again, remember, this is the universe to Aristotle. So that applies too. It makes sense. It's a pretty sensible view. However, do any of you see any problems with, in order to make something move horizontally or make something move unnaturally, you have to supply a force to it. And when you stop supplying force, it stops moving. Can anyone think of a problem with this scenario? What if this was the scenario? What if you took a baseball and you threw it? How does that fit with Aristotle? How is it that a baseball can move, right? Is it being forced to move in a non-natural way? Initially, okay. And that's sort of what Aristotle would have said. You put force in, and the ball will continue to fly until the force runs out, and then the ball will transition and fall straight down into natural motion along this path. Is this the actual path that a thrown baseball will take? Uh, it's actually not. It's actually not. It's sort of like that, but not really. In fact, if you examine it closely and you say film it, yeah, and also we have to remember, right, that we are in an air environment, so the spin of the ball definitely affects how it flies. But if you say took a baseball and you threw it with like no spin, um, you would find that if this is the straight path, the ball actually follows a parabolic path to the ground, right? It doesn't go straight out and then transition to straight down, the way that Aristotle thought. It's subtle, but with some experimentation, it's easy to prove that it does not fly like this. So even in Aristotle's day, uh, people had a little bit of an issue with this violent and nonviolent motion because it doesn't actually fly like this. You can actually look and find. I've seen pictures, and it's like medieval archers, shooting arrows, and the picture that they show is literally like a straight line, okay, like this, and then a straight line like this, and they're saying that the arrow, what it's doing, is it's just coming off of this and then doing that, okay? That's not really how arrows fly, but it's close, okay? Now remember what we said about Aristotle a long time ago. He was a natural philosopher who believed all knowledge was already in everyone's brain. And just by thinking about things, you could essentially figure out how the world works. That's not the way that science is done today. Today, we do experiments, and then we come to conclusions, right? After we see what the experiments say. Or we have, a hypothesis or a theory, and then we go out and test it. In Aristotle's day, although he's kind of doing science in that he's trying to understand the world from the human perspective rather than from the, say, supernatural perspective, his technique of doing science was a lot different than what we would consider to be science today. So he never actually tested any of these ideas, right? He didn't test it. Didn't test. Okay? But his influence was so strong that that didn't really matter. People just kind of took it, as the truth. Now, here's something else Aristotle said. He said, the heavier an object, the faster it falls. Does anyone have an issue with that? Because you should. Okay? So let's think about this. Aristotle said, like, let's say I take a small ball, and I take a ball that weighs 3 times as much. Okay? And I drop them. What he said was, if this is the tabletop here, okay, this object, being 3 times heavier, would get to the tabletop 3 times faster. That is clearly not right. Take two things right now that weigh different masses, take a pencil and a book, hold them up high, and drop them at the same time and see what happens. Does the book, which weighs probably 10 times what your pencil weighs, does it actually get to the ground earlier? No. Okay? So lots of experimenting going on. So we get, like, it's not hard even for, high school students to see that there was a problem with this. And yet Aristotle wrote this down, and this stayed as sort of like canon essentially for, the next, I guess, probably 1,000 years-ish, something like that. Now, there's a lot of political reasons why that happened, which we're probably not going to end up getting into. Part of it had to do with the, essentially, like the conquest, I guess, of Greece by Rome, or the absorbing of Greece into the Roman Empire. Then following that, you had the Dark Ages. So there's lots of chaos and stuff, at least in Europe. But really, science didn't seem to advance a lot for many years. This is sort of the where it stayed at, really, until Galileo came along. And we'll talk about Galileo in another video. But there's a really good video about the feather and the hammer on the moon. But we'll talk about that more when we get to Galileo. So there you go. There's sort of Aristotle's views, more or less, on the way that physics worked and on the way that objects moved. So